In this video, we will introduce the notion of an eigenvalue. This topic can be found in section 6.1 of our text. So one of the most important problems in linear algebra is something called the eigenvalue problem. And it goes like this. If A is an n by n matrix, a square matrix, do there exist vectors x and r to the n such that ax is a scalar multiple of x, meaning are there vectors x so that ax equals some scalar lambda times x. So lambda here is a real or a complex number that we call the eigenvalue of the matrix A, and the vector x in r to the n is called an eigenvector of A, corresponding to the eigenvalue lambda. Now, note, eigenvectors are never allowed to be the zero vector. Let's see why. If you take any matrix A and multiply by the zero vector, you will always get the same thing as lambda times 0. You'll get 0, and that's going to be true for every possible real and complex number lambda. And so since it's true for every possible lambda, this statement is meaningless. So we do not allow eigenvectors to be the zero vector. However, eigenvalues lambda may be the number 0. Also, geometrically speaking, keep in mind if we say that ax equals lambda x, then what that means is we're talking about parallel vectors, vectors that are parallel to x, right? So if this is the vector x that we see here, and we multiply by a positive scalar, so a positive scalar is a vector that's going to live on that exact same line and point in exactly the same direction. The length of the vector may change, but not the direction. Or if we multiply by a negative scalar, then it'll still lie on the same line as the original vector x, but a negative scalar would just change it so that it points in the opposite direction. So we're saying we want to take a vector x, we multiply by a, we want to end up with a vector that lives on the same line as that original vector x. That's the picture geometrically that we're working with. Okay, so here's our formal definition. Let A be an n by n matrix. The scalar lambda is an eigenvalue of A if there exists a non-zero vector x such that ax equals lambda x. The vector x is called the eigenvector of A, corresponding to the eigenvalue lambda. So here's an example. Consider the 2 by 2 matrix for negative 2, 1, 1. And let's verify that the vector 2, 1 is in fact an eigenvector of A and find the corresponding eigenvalue. So what we need to do is we need to consider the product A times X. We've got our matrix A times the vector X. A quick matrix multiplication shows us that we will get 6, 3, which is of course 3 times the vector that we started with, 2, 1. So therefore, the vector 2, 1 is, in fact, an eigenvector of A, and the corresponding eigenvalue in this case, lambda, would be 3. So it's pretty easy to verify whether a given vector is or is not an eigenvector of a specific matrix. So the big question is, how do we go about finding these eigenvectors and eigenvalues in the first place? That's going to be the focus of where we head next. But before we get there, we do need one last little piece of theory. So 2 facts. If A is an n by n matrix with an eigenvalue lambda and corresponding eigenvector x, then for any scalar c, c times x will also be an eigenvector of A. Let's see how that works. So if we look at A times the scalar multiple cx, we are allowed to pull that scalar out in front and think of this as c times ax. Now, because x is an eigenvector of A with eigenvalue lambda, by definition, that tells us that ax is equal to lambda x. So this becomes our scalar c times lambda x. And we can multiply those scalars in any order that we like. So we can rearrange this as lambda times cx. So we see that cx is again an eigenvector of A with eigenvalue lambda. Secondly, if I have two eigenvectors, x1 and x2, with the same eigenvalue lambda, then the sum x1 plus x2 will again be an eigenvector of A. Let's see why that is true. So if we apply A to the sum x1 plus x2, we can distribute our matrix multiplication. The fact that x1 is an eigenvector of A with eigenvalue lambda means that ax1 is lambda x1. The fact that x2 is an eigenvector of A with eigenvalue lambda tells us that ax2 equals lambda x2. We then, of course, can pull out the lambda. And so we see that the sum x1 plus x2 is an eigenvector of A with eigenvalue lambda. Okay, now think back. If we're talking about being closed under scalar multiplication, closed under vector addition, I hope this is sounding familiar to you, that we are talking about some sort of subspace, right? So if A is an n by n matrix with an eigenvalue lambda, and we look at all possible eigenvectors associated with the eigenvalue lambda, we get a subspace. We get a subspace of Rn called the eigenspace of lambda. Great. Notice here, because we said previously that eigenvectors are not allowed to be zero, but that in order to be a subspace, it must contain the zero vector, then we've just kind of included that in our definition. We said for our eigenspace, we're going to take all those eigenvectors and throw the zero vector in there just so we have a nice, well-defined subspace. Okay, so now the important thing. Let's find a procedure for finding eigenvalues and eigenvectors. So we've got our main equation here, ax equals lambda x. That's the key to everything, right? So what we're going to do is we're just going to subtract the ax over to the right. So we get 0 equals lambda x minus ax. Or if you want to make things look a little more like two matrices being subtracted, we can write that as 0 equals lambda times the identity matrix I times x equals lambda x. We can factor out that vector x. And so now we have a nice matrix equation. And if you think back to our main theorem, our equivalent conditions for being an invertible matrix, what we in class called the big hammer theorem, then this equation, the system, has non-zero solutions, non-trivial solutions, if and only if lambda I minus A is not invertible. So if and only if the determinant of lambda I minus A equals 0. And that's the key to the whole thing. So here's our big theorem. If A is an n by n matrix, then an eigenvalue of A is a scalar lambda, such that the determinant of lambda I minus A is 0. And then the eigenvectors of A corresponding to lambda are the non-zero solutions of the equation lambda I minus A x equals 0. Great. So we've got the theory and our introduction behind us. In the next video, we will do some concrete examples in the case when our eigenvalues are real numbers. And the third video, we'll look at complex valued eigenvalues. That's all for now.